Good day, everybody. Today, we'll be talking about transition metals. As we have learned before, many of the metal elements in the periodic table are essential for good health. However, the form in which the metals are consumed is important. For example, iron in fish and meat is more readily absorbed by the body than iron in vegetables. In this chapter, we'll explore how the chemical environment of metal ions in solids and in the solutions affects their physical, chemical, and biological properties. We have learned previously about Lewis acids and bases. We defined acids and bases in terms of their ability of substance to donate a lone pair of electrons, and we define this as the Lewis base, or to accept a pair of electrons. That's Lewis acid. The Lewis definition allows us to extend the concept of acid-base behavior to explain the behavior of metals in the reaction and to situations that do not involve proton transfer. For example, let's look at the picture below. The reaction between silver ion and the Lewis base, ammonium, happens in such a way one ammonia donates a pair of electrons to silver, thus formed two new bonds as indicated over here. The electrons donated by ammonia only, they are shared between silver and ammonia, and those two bonds are so-called coordinate covalent bonds, and we will go into the details a little bit more. The sharing of an electron pair in which both electrons are donated by one atom, in this case that's the nitrogen from ammonia. As you can see in the previous example, a coordinate bond is a bond formed when one anion or one molecule donates a pair of electrons to another ion or molecule to form a covalent bond. Once formed, it is indistinguishable from any other covalent bond. Let's look at this for one more time. As you can see in this example, the newly formed bond has two electrons that is shared, but those two electrons, they exclusively come from the ammonia, which is the ligand over here. So what is a ligand? A ligand is a Lewis base, which means they donate a pair of electrons. Okay, is a Lewis base bounded to the central metal ion or a complex ion. What is a complex ion? Complex ion is ionic species consisting of a metal ion bounded to one or more Lewis bases. What about counterions? Counterions are ions that balance the electrical charges of complex ions in coordination compounds. So what is a coordination compound? A coordination compound is any compound that has the complex ion and the counterion together. Coordination number identifies the number of electron pairs surrounding the metal ion in the complex. Let's look at another example so you can better understand these terms. Consider what happens when metal salt dissolves in the solution containing ammonia. For example, a cobalt salt dissolves in ammonia. When the salt dissolves, it forms the free metal ion, which can then engage in the Lewis acid-base reaction with ammonia. And here is the product that is formed. In this process, ammonia serves as the Lewis space because each of them donate a pair of electrons to the center cobalt ion. Because all of the electrons used to form the bonds between ammonia and cobalt come from the nitrogen atom on ammonia, the resulting bonds are coordinate covalent bonds. The complex ion carries a charge which is 3+ charge. This ion is a complex ion. And the charge must be balanced with the counter ions, which are the chloride ion. That's the counter ion. So complex ion. The counter ion balance the charges because you have a 3 total plus charge. So you need the 3 chloride to balance the 3 plus charges. So these ions are counter ions. And this compound together, if you write it using the bracket CONH3, 6 of them, and then you have a CO3. And this compound is going to be called the coordination compound. For the example on the right side, the ligands, out of the 6 ligands, 5 of them are ammonia molecules, and the other one left is the chloride ion. To balance the electrical charge, we have 2 chloride ions. So in this case, this will be the complex ion. Then the chloride is still the counter ion, but you only have 2 counter ions over here. So when you put it together, the coordination compound would be CONH3, 5 of them, and you also have a chloride. You put the complex ion in the bracket, and then the counter ion outside the bracket, as you can see in these 2 examples. Examples of several more coordination compounds are provided in this table, along with their coordination number and shape. As you can see, for these compounds, each ligand donates 1 pair of electrons. So you have 6 ligands. If you have 6 ligands, because each one donates 1 pair of electrons, and the coordination number is defined as pairs of electrons surrounding the central metal. So you have a coordination number of 6. So similarly, ammonia only donates 1 pair of electron. So you have 4 ammonia. Coordination number will be 4. A similar situation happens for the other 2. The shape of the molecule depends on 2 factors. One is the coordination number. The other one is the type of ligands. For example, if you have a coordination number of 6, then it's usually octahedral shape. If you have a 4, it could be a square planar. For example, when you look at this complex ion. Or it could be tetrahedral, as you can see in the zinc complex with water. When you have 2 ligands, the geometry or the shape is going to be linear. Next, let's go into the details about how to name the coordination compounds we just talked about. And this topic is extremely important. It will be tested in your exam. First thing you need to understand is when we name an ionic compound, no matter if it's the simple ionic compound like sodium chloride, potassium sulfate, etc. When you name any ionic compound, including the ionic compound containing complex ion, also called coordination compounds, you always name the cation first, then you name the anion. For example, when you have a complex ion and a counter ion, this is counter ion, complex ion. Remember, the complex ion is always included in a bracket. You see it in the brackets. See that? Complex ion and the counter ion. What you need to do is you always name this is counter ion, this is complex ion, counter ion, complex ion, complex ion, counter ion. So you have the cation name first, then you have the anion, as if you are naming something like sodium chloride. Sodium means it's sodium ion. Chloride means it's chloride ion. We drop the ion portion and put together the ionic compound name. For the coordination compound, it's exactly the same way. Look at the second example. Potassium means that's potassium ion. And hexacyanoferrate, that means you have this ion. Of course, we are going to talk about how to name these complex ions. Okay, so if you know how to name the complex ion, the counter ions are usually easy. Okay, so this is complex ion. Counter ion is called a bromide. We never say dibromide because it's what we have already learned. So never use di-tri for the ion themselves. But in the complex ion, we do need to use them to indicate how many ligands we have. So let's look at the details. The first step to name the complex ion is first you name the ligands. If you have more than one type of ligand, then you will put them in the alphabetical order. And the ligands, they are slightly different from the original anions. For example, if a bromide is serving as a ligand, it becomes bromo in the complex. If it's a chloride, it becomes chloro. They have O ending, as you might have noticed. If it's hydroxide, it becomes hydroxo. If it's cyanide, it becomes cyano. Nitrite becomes nitro, etc. These are anions, ligands. And for neutral molecules, you need to actually memorize these things because you'll be asked to use these names in the naming. For neutral molecules like water we call that our. And NH3, which is ammonia, for the neutral molecules. But in the ligand name, in the complex ion, it becomes amine. Remember, you do have a 2M over here, right? Next, the carbon monoxide, it becomes carbonyl. And the ethylene diene, we can simplify this as EN. Okay, ethylene diene, we'll talk about that in a little bit. If you have more than one type of ligands, for example, if you have both bromide and the chloride ions serving as ligands, then you need to use bromo and chloro in the name of the complex ion. At the same time, you do remember bromo, which has a B as the first letter, this will be put before chloro, etc., because we have to make sure all the ligands are arranged alphabetically. Step 2, use the prefixes to indicate the number of ligand. It's the number of ligands that you have. For example, you use di to represent 2, and a tri for 3, tetra for 4, penta for 5, hexa for 6, etc. After identifying the name and the number of each ligand, we identify the central metal ion. And we make sure if the complex ion is a cation, then we use the name of the metal followed by a Roman numeral in the parentheses to indicate the charge of the metal ion it carries. So let's look at the example below. For example, in this complex ion, it carries 2+ charge. And this 2+ charge is not the charge for the metal. This is the complex ion charge. How do you calculate the metal charge? The metal charge can be calculated by considering the complex ion charge and the charges of the ligands. So for example, what's the charge for nickel here? We do remember the total charge for complex ion, as you can see over here, that's 2+ charge. And we do know you have 6 water, and each water carries 0 charge because they are neutral ligands. So for this reason, this 2+ charge for the complex ion will be the same in this case for nickel. So that's why nickel carries 2 charge. And let's put this together. We only have one type of ligand here, and this is water. In the complex ion, we call this awa. And you have 6 of them, so we have hexa-awa. And then we name the nickel metal ion, and we do know nickel carries 2+, which is this charge. That's why we call this hexa-awa nickel 2. Let's look at the next example. Similarly, when you look at the next example, this charge is the complex ion charge. That's not necessarily the metal charge. Okay. And how do we figure out the metal charge? So the metal charge, we don't know yet. It has to be calculated based on the ligand charge and the complex ion charge. And the ligand here is ammonia. You have 6 of them, and each ammonia carries 0 charge because it's a neutral ligand we are using. So for the same reason, this cobalt carries 3+. This carries a 3+ charge. So for this reason, we name the ligand first. The first step. This is ammonia, but in the complex ion, we call this amine. And you have 6 of them. That's why it's hexaamine, cobalt 3. This 3 comes from the metal charge. Now let's look at a different situation. What if the complex ion is an anion? Remember, the metal ions will always be cation. Okay? The metal ion will always be cation. But when you are part of the complex ion could be negative charged. For example, let's name this compound K3. Then we have FeCN5Cl. How would you name this compound? Apparently, the left side, that's the counter ion. We have a 3K+. These are counter ions. Okay. The right side, that's FeCN5Cl. And this ion, it carries 3 minus charge. How do we know? Because the total charge for the counter ion is 3 times 1+. So that's a 3+ charge. To cancel that out, this ion must be 3 minus. So now we need to figure out what the metal ion charge carries. Okay. So basically a CN, what charge does CN carry? CN carries 1 negative charge. Okay. And you have 5, this is a -1, and you have 5 of them. And Cl comes from chloride, which is called a chloro. Okay. It also has a -1 charge, and you have 1 of them. Right. So what charge should this Fe carry? So -5 plus -1, that's -6. But the whole complex ion carries -3. Okay. So this 3 totaled, that must be -3. So for this reason, this iron would carry a +3 charge. So that question mark here would be 3+. So for this reason, this is a 3+ charge. But the difference is, if the complex anion complex is an anion, we need to drop the ending of the metal and add ATE followed by the oxidation state with the Roman numeral. So basically, for example, rather than calling this, if the complex ion is cation, we used to call that what? We used to just call that a cobalt 3. Still remember that? Right, in the previous example, that's exactly what we call. We call this a cobalt 3. Okay. However, if the whole thing is an anion, similar to this one, if it's a cobalt, you do not call that cobalt 3, rather you're going to call this cobaltate, because you add ATE. Okay. Then you're going to call this cobaltate 3 if it comes from Cu3+. For this example, it would be called cobalt 3 if the complex ion is a cation. But if it's an anion, then this will call it cobaltate 3. Okay. Similarly, for the iron, if it's 3 charged, if it's a positively charged ion, like you can see over here, for example, if it's nickel 2, it would be called a nickel 2. If it's iron 3, for example, if it's iron 3, for cationic complex ion. Okay. Then this Fe3+, it would be simply called iron 3. Okay, of course, as part of the complex name, like this, as part of this complex name, as part of the whole thing. Okay, but if it's in the ionic complex, okay, for anionic complex, it will be different. Rather than calling this iron 3, we will call this a ferrite 3. So ferrite, indicating this complex ion is an anion, so we call this ferrite 3. So for this reason, if we put all of this together, this is anionic because this is an anion for the complex ion. So when we put everything together, let's do this for one more time. Right? Let me now follow this step by step. First step, we got to indicate what kind of ligands you have. Cn minus, the cyanide ion. In the complex ion, you call this cyano. Right. Then the Cl minus, we call this is chloride ion. However, in the complex ion, we call this chloro. So when you put it together, it would become this. Because the first thing, you name the cation first for the whole thing. So the cation is potassium ion. We don't call that tripotassium. Okay, it's simply called potassium. Right. Potassium what? Potassium followed by the complex ion name. And this complex ion is, we do the ligands first. And cyano is actually, alphabetically, it should be behind the chloro. So we're going to do chloro first. So it will be chloro. Then you have 5 cyanide. Notice that we do not say monochloro, simply say chloro. Okay, so 5 cyano. That means it's pent cyano. And then we need to name the anion here. You need to name the iron here. Okay, but this is anionic. So for this reason, this iron is not called iron 3. Rather, it's going to be called a ferrite 3. So and it's going to be ferrate 3. So that's how we name the metal ion if it's part of the complex anion. Let's put everything together. You have seen this slide in the very beginning. So put this together. That's the complex ion, which is put inside the bracket. Then you have an anion. The anion over here, apparently that's called a chloride. This is counter-ion, so you don't call this chloro because it's not part of the complex ion. This is called a chloride. And the left side, how do you name this guy? So basically, you got to do this stepwise. Each NO3 is called amine, and you have 6 of them. Okay, 6 times of this, and that's only one type. So for this reason, we call that a hexaamine. Step 2. So step 1, you name this alphabetically. Step 2, put a prefix before it. And step 3 is going to be the metal ion. And the metal ion is part of the, because this whole thing, when you write it, if you write this ion only, it would carry a 2+ charge. So this is a cation. Part of the cation, nickel, would be called a nickel 2. Okay, so that's why it's called a nickel 2. Then you have chloride over here. If it's part of the anion, it would not be called a nickel. Okay, rather it would be called a nickelate 2. But here it's part of the cation, complex cation. So for this reason, it's nickel 2. Then you have the counter-ion named. Right. Look at the next example. This example, this is K+, and the other side is the complex ion, and through the charge, because you have 3 of them, so you do know you have 3- charge, and then we can figure out Fe carries a 3+ charge. So let's do this. First, we name the cation. It's called a potassium ion, and then the complex ion is the anion. Okay, do remember Cn is called a cyano. That's the step 1. You name the ligand. Then you put the prefix 1, 2, 3, 4. No prefix for 1, but 2 is di, 3 is tri, etc. Okay, we have 6 of them, so that's why this is called a hexa. Okay, hexacyano. Then the next step, step 3, is the cation itself, the metal cation. And the metal cation, it is Fe3+. If you single it out, it would be Fe3+. But we don't call this iron. If you do iron 3, that's wrong, because this is actually for a different type of naming. Look at that. Here is this is an anion. The complex ion is an anion. So you don't do iron 3. Rather, you do ferrate 3. So that's why you get the name ferrate 3 rather than iron 3, because this metal ion is a part of the anionic complex ion. All right. So you can actually look at the next in a similar fashion. First step, you got to know which one is anion, which one's cation. So when you, in the bracket, this one is a complex ion, and it is cation as well. So you can actually single this out. So inside the bracket, you have CO, NH3, and you have H2O. Notice if you have a ligand that has more than one letter, you actually put them in the parentheses. Okay. Then you put a bracket, because Br carries -1 charge. So 2 of them will carry 2 negative charge. To cancel out the 2 negative charge, this must be 2+ charge. Okay. And the anion is 2 Br-. Br- is called a bromide. Okay. Then the complex ion, remember this is a cation. Okay. This complex ion is a cation. So for this reason, you name the ligand. The ligand is amine, and our. Our alphabetically should be put this before. Amine should be put this before our. All right. So penta-amine, our, cobalt 2, not cobaltate 2, because this is this complex is a cation. All right. Okay. Let's look at 2 more examples stepwise. All right. So first thing, look at this example. First, you identify following the same procedure as we just did. So look at this cation plus the anion, which is the counterion, and we do know what is called our. This chloride is called a chloro in the complex ion, and because this metal ion is part of the cation. See, this is a cation over here. So for this metal ion is part of the cation, so we simply call this a chromium 3. Okay, so we put everything together. Do remember our is actually so this should be our. Okay, our is actually before chloro, so we call this penta our, and then you have chloro. Then it's chromium 3. Okay, put everything together. Penta again, it's our. This O should be A. Penta our, chloro, chromium 3, chloride. This chloride again is the counterion, so you don't call this chloride chloro, or else it would be wrong. Okay. Now let's look at the different situation. For example, this situation we actually talked about similar ones. So you do identify K plus as the potassium ion, which is the counterion. Okay. So we do know the complex ion carries a 3 minus charge. Complex ion is actually an anion here. So Cn minus is cyanide, but in the complex ion you don't call this cyanide, you call this a cyano. You got to memorize that. All right. So the step three, the metal ion as part of the anion, because the whole thing over here, look at that, that's anion. Look at this is 3 minus charge. So this complex ion is an anion. So for this reason, this iron 3 plus is not called iron 3, rather it's called a ferrate 3. Right. So put everything together. This complex ion is a hexacyanoferrate 3, and the potassium ion is a cation. You always name cation first, so it's called a potassium hexacyanoferrate. Hopefully this helps you understand completely how to name the coordination compounds. All the ligands you have seen so far, for example, cyano, amine, ammonia serving as the ligand. That's amine, right? Then water serving as ligand. It's called awa, and all of them only provide 1 pair of electrons. So if they only bond to the metal ion, okay, using a single coordinate bond, or you donate 1 pair of electrons. So it's 1 pair of electrons. For this case, we call them monodentate ligand, like water, and ammonia, and chloride. They are monodentate ligand. But the species that can form more than 1 coordinate bond, then you call that polydentate, which means they can donate more than 1 pair of electrons. For example, for this ethylene diamine, in this structure, apparently each nitrogen can donate a pair of electrons. So this is actually so-called a chelating agent, because it can provide more than 1 pair of electrons, and it's called a polydentate ligand as well. Okay, so you might have ethylene triamine. This one can provide a 3 point of attachment. Then this one is also a polydentate ligand. Let's look at one example. For example, nickel can form a complex ion with the ethylene diamine. All right, this is ethylene diamine, by the way. And ethylene diamine, a lot of times we can simply abbreviate this as EN, as you can see over here. You have 3 ligands, but each ligand provides 2 pairs of electrons. So for this case, all right, you have coordination number. This is not 3, it's 3 ligands, but each ligand provides 2 point of coordination bond. So this is actually 6. Okay, so when you name this, this is called a triethylene diamine nickel 2. This nickel carries 2 plus charge over here, and this whole ligand is neutral. Okay, here's the structure on the right side of this complex, which looks very beautiful. As you might imagine, larger molecules with multiple lone pair donors are capable of forming more than 3 bonds. In addition, other lone pair donor groups can be utilized. For example, in EDTA, you have 2 nitrogen donors and 4 oxygen donors. In total, it can form 6 coordination bonds. So as shown in this slide, one EDTA molecule is capable of wrapping around a metal cation and forming coordinate bonds at all 6 octahedral bonding locations. For this reason, EDTA forms very stable complex ions and is often used as sequestering agent that prevents the metal ion from reacting with other substances. It's used as a preservative in many beverages and prepared foods to prevent metal ions from catalyzing the degradation of food ingredients. Many complex ions show different colors. The reason is because part of the spectrum is being absorbed. For example, on the color wheel, if the red light is being absorbed, then opposite to that color on the wheel, green color will show as the color of the substance. Similarly, if a blue color is absorbed, and orange color will show up, etc. Let's look at some examples. For example, when red light is absorbed, in this case, then green light will show up, as we just explained in the color wheel. Red light absorbed, so green will show up. And then if orange light is absorbed, blue will show up. Orange absorbed, so blue will show up. Look at one more example. If yellow is absorbed, then purple will show up. You see, yellow is absorbed, so purple will show up. The complex ions usually will show different properties. One property is magnetic properties. When it shows paramagnetism, we say it has the ability to be attracted to the magnetic field. And this requires unpaired electrons in the metal ions. We will not go into the details about it, and you are not required to go into the details either. Some complex ions will have stereoisomers. For example, diamine dichloroplatinum 2 ions. They can show 2 different structures. And in one of the structure is called a cis, because both of the same ions are on the same side. But if they are on the opposite side, 2 ammonia on the opposite side, 2 chloride ion on the opposite side. Okay, so in this case, we call them trans isomer. Please notice both of the isomers are existing in the square planar shape. Similarly, we can observe stereoisomerism in octahedral complex. For example, in this tetraamine dichloro cobalt 3 chloride compound. Okay. The complex ion portion, which is in the bracket, can have cis, which means the two chloro are neighboring each other, or trans geometry, and they show different colors. Another type of isomerism discussed previously was optical isomers. Those are the compounds that interacted with the plane polarized light in such a way that the two isomers rotated the light in the opposite directions. And these isomers, they are the mirror images of each other. In this case, we call them enantiomers, which is defined as the non-superimposable mirror images of each other. In this slide, we have several polydentate ligands that are important in biological systems, and these are the tetradentate ligand system, because we see 4 different donors in each of them. The first one is called a Chlorin, and the second one is called a porphyrin, and they are all in the ring system. When metal ion forms a complex ion with them, metal ion actually sits right in the middle. Chlorins and porphyrins are common in many biological systems. The chemical and the physical properties and functions of the metal complexes depend on the identity and the charge of the central metal ion, as well as the other functional groups that might be attached to the macrocycles, or the macrocycle means a big ring. We are going to talk more about different transition metals serving different functions in the biological system. For example, iron and zinc are the only transition elements that are considered as trace essential elements, and the transition metal cations form a coordination complex by bonding to nitrogen atoms in the amino acids of proteins. Many of the enzymes in our bodies contain zinc or iron or other transition metals, and these kind of enzymes are called metalloenzymes, or enzymes containing metals. So they are called metalloenzymes. Zinc is incorporated into the active site of the carbonic anhydrase enzyme that is responsible for the formation of carbonate, which is critical in the elimination of carbon dioxide from the cells. Iron is incorporated in the hemoglobin, which is vital for oxygen transport in the body. Other iron-containing enzymes do exist as well. This figure shows the location of the zinc cation in the active site of the carbonic anhydrase. That's where zinc is. The zinc cation is complex with the 3 histidine residues and the 1 water molecule. This is 1 water molecule. That's a histidine residue. An important porphyrin complex that is called the heme group contains the coordinated bonded iron 2 cation. The heme group enables protein, hemoglobin, and myoglobin to transport oxygen in the blood and store oxygen in muscles, respectively. Molybdenum and vanadium are involved in important components in many metalloenzymes. For example, molybdenum can be found in the xanthine oxidase, which degrades the excessive amount of nucleic acids. Copper-containing proteins perform several functions in both plants and animals. Copper is important in oxygen transport in mollusks, for example, clams and oysters. Copper is also an important component of the enzymes azurin and plastocyanin, which mediate the electron transfer reactions during the photosynthesis. Copper is also involved in the enzyme that is responsible to convert superoxides to hydrogen peroxide. Superoxide convert to hydrogen peroxide. Nickel is an important component in ureases, which is responsible for the conversion of urea to ammonia in plants, and in hydrogenase enzymes responsible for the oxidation of hydrogen to H+ ions. Cobalt is part of a coenzyme, cobalt coenzyme. So what is a coenzyme? A coenzyme is an organic molecule that accelerates the rate of a biochemical reaction by cooperative action with an enzyme. For example, the coenzyme B12 is a derivative of vitamin B12 and contains cobalt. This is critical to the function of mutases. Mutases are the enzymes that catalyze the rearrangement of molecular skeletons. Manganese is a very essential component in chlorophylls. It also mediates the transfer of electrons from water during the photosynthesis. Chromium is involved in the chromodulin for the regulation of glucose levels in the blood. All in all, of the 30 or so essential elements, some are also useful for diagnostic and therapeutic applications. In addition, there are many other elements, including radioactive isotopes, that are used in the diagnosis and the treatment of a wide range of illness. Any diagnostic or therapeutic compound that is injected intravenously must be sufficiently soluble in blood to be delivered to the target. It must also be stable enough to not undergo chemical reactions that may result in its elimination from the body. In some cases, the compound may be in the form of salt to increase the solubility in water or the blood, or it may involve the formation of a coordination complex in the case of metal cations. Some of the ligands used in the formation of coordination complexes in the diagnostics and the therapeutic area are listed in this slide, as you can see over here. Medicinal chemists can take advantage of these substances that occur naturally in the body, such as antibodies, to carry out a diagnostic or therapeutic metal ion to the target. And the element technetium 99 is kind of special because it has no stable isotopes. Technetium isotopes can be produced in nuclear reactors for use in medicine. Radiant compounds are being studied for use as both imaging agents and as therapeutic agents for many tumors, including breast, liver, and skin cancer. Several lanthanide series elements are used in diagnostic applications as well. Many of the imaging applications that utilize lanthanide isotopes are listed on this slides. You don't need to go over the details of everything. Do remember, not all imaging applications involve the radioactive nuclides. A stable isotope of gadolinium is used to enhance the images generated in MRI. Examples of an MRI image before and after the enhancement of gadolinium is shown over here. This is unenhanced. That's enhanced image with gadolinium. Compounds of some transition metals demonstrate anti-tumor activity, including the coordination compounds of titanium, vanadium, and niobium. These compounds contain carbon metal bonds and they are classified as organometallics. Unfortunately, the dosage needed for therapeutic efficacy may also increase the risk of liver damage, which limits the benefits. Soluble coordination complexes of platinum group metals are used in the medication for arthritis, cancer, and other diseases. To sum it up, transition metals have been widely used in the diagnostics and the therapeutics in the medicine area. You are not required to know all the details about how those compounds are used. That's it for today, and have a good day. Bye-bye.